Believe it or not, this small solar electric array is enough to produce significant reductions in the air conditioning loads of this nice house. Electricity produced by it is used immediately on any given hot summer day by producing bathtubs full of cold water. These tubs of cold water are the battery that store the sun's power for use by the building. The reason why we're using water is because Tesla batteries are expensive as compared to that blue tank, which is only $2,500 versus $7,500. Our system uses these 50-gallon plastic tanks, which, when insulated well, is lower in cost and way more effective than the big blue tanks. And when combined with certain geothermal source configurations, even more storage potential can be realized. The tanks can also store hot water for use in winter to heat the home. The least significant, but also very important, is the effect of a well-designed passive solar home or building that will contribute to the total storage cachet. Thermal mass of a well-designed solar structure delivers storage from contents within the building more directly to the residents, and this added capacity usually comes at no or little extra cost. But the most significant advantage to our solar heat pump system with our solar heat pump module is a little thing called coefficient of performance, and it's a magic little thing that comes with any air conditioning compressing system. Because a heat pump extracts heat from sources rather than just converting electricity to heat, and in most cases 3 to 5 times more efficient at using the electricity that comes sparingly from the sun in our solar heat pump module configuration. That number, 70, is the goal. It's the value that costs the most. It's the target we can use for our solar heat pump module to extract heat or cool to do the most good. The heat or cold is extracted directly from our tanks when it's needed by the house. Our solar heat pump design provides superior economics and performance. Powered by a 1 to 5 kW photovoltaic array, it can provide up to 90% of a home's heating and air conditioning loads. Designed to use geothermal sources, it will qualify at this point in time for both solar and geothermal federal tax credits, making it a very economical system. Solar geothermal HVA systems designed with the solar heat pump module can be adapted to new or existing homes and are especially effective in northern climates. Solar heat pump module systems work very well with existing passive solar and earthship or solar home designs. Solar heat pump systems can also operate completely independently of any AC grid connection and can provide backup heating and cooling in a power outage. Okay, that's a lot said. Maybe you'll understand it better while we show you some of the components of the system. Sunny or cloudy, the solar panel powers a DC motor which is connected to a conventional automotive AC compressor. That big flywheel smooths out any variations in solar caused by clouds. The compressor circulates a refrigerant that, just like your AC in your car or home, pulling heat from one place to another to heat or cool. The compressor heats one tank at the same time it cools another, with simple metal tube loops immersed in water. It works all day as long as the sun shines enough to power the motor. Pumps then circulate the warm or cold water to the home's HVAC system to either heat or cool depending on the season. And of course it works all quite too well with super duper microprocessors and controls connected to your home's thermostat. Okay, let's start with an example. In the summertime, gains in the heat tank are drained away by a solenoid valve into the sump pits of the house. The sump pump may expel it outside, or it may linger and distribute heat to within the drain tile system. The hot tank will then be refilled with sump water, well water, lake water, or any other water source available as the cooling source for the solar heat pump module. At the same time that the heat is being generated in the hot tank, cool generated in the cold tank is circulated with a pump and a thermostat to a radiator heat exchanger located within the home's standard HVAC system. And the hot and cold on the other side is now deposited into your sump pit system. And of course, it's all done absolutely free, powered by the solar panels. This works every sunny day, partly cloudy day, or stormy day, cooling as much as it can till fall and winter. And of course, in the winter, the supply water for the HVAC is changed to the hot side. Now, cool is expelled to the sump. And here's where we're going to just digress a minute. Let's take a look at a typical sump system that we have here in Wisconsin. A specialized pump removes water collected in a tank that's at the deepest part of a drain tile field below a basement floor. The water is extracted to the outside of the building to a discharge point, usually far enough away from the house so that it does not continually circulate. If it did, one might expect, as it did circulate, it might extract some heat or cool from the soil, crushed rock, or concrete that it passes by along the way. Wouldn't that be something? And let's say we had a dual sump pit in our Wisconsin home so that we could put heat pump source water in one side and out the other, thereby expanding our geothermal cooling capacity by affecting tons and tons of thermal mass 8 feet below the ground. This has got to work, and it would work well with just about any proper sump pump system here in Wisconsin. You'd be using the underground portion, the mass in your basement, for geothermal heating and cooling throughout the year. It's the perfect thermal battery, and it works perfectly with our solar heat pump modules. In a typical 3-bedroom ranch in Wisconsin, this dual sump pit basement could be as good as 160 feet of geothermal loop that has to be done by an excavator. These loops are the things that comprise the bulk of the cost of geothermal heating and cooling. You might wonder if the basement's going to be enough to provide all the needs that we have, but just wait, there's more. This loop in the basement gets recharged regularly, especially when it rains or if a warming trend melts snow in the winter. Many residents in my Wisconsin community find their sump pumps running all winter long, providing a needed source of all sorts of earth-warming water. And of course, spring, summer, and fall rains extract loads of earth cool for summer air conditioning needs. And you got to remember that this is just a solar heat pump module, which is an addition to your existing heating system. It doesn't do the whole geothermal system of the house. And it's really hard to find data or understand just how much contributions from rainfall and snowfall are going to have on this sump pump system. But here's a graph of the temperatures you might see in winter on the hot and cool tank of your solar heat pump module. As the sun gets stronger, the heat pump provides heat to the hot side. And in a solar home design, it can sock away heat all day, getting up to 85 degrees from a starting point of 72. At the same time, of course, it's extracting heat from the cold side and essentially from the sump pit supply. Heat is only extracted from the sump pit during the day during solar hours, so it has a chance to recover perhaps by the next morning at 6 a.m. to a point at which it's right back to where it started the day before. And of course, at the same time, In an ideal situation, all the heat from the hot tank is delivered through the night to the home. This is perfectly suited to a passive solar home like this one, where the living space is heated by direct gains through south-facing windows all day long. It really only needs heat at night. The heat then comes from the stored solar thermal heat in the heat tank and provides it throughout the night until it's totally exhausted. Spring and fall, this system's going to work very well and provide all the heat that's going to be needed by this house on a typical given day. Bright sunny skies generally come with those below zero temperatures in January and February, so there's always some relief from the solar system. And of course, that's why a backup auxiliary system, typically in this climate, gas, provides the balances. Okay, let's talk about those tanks. There's two of them. They're hooked to the solar heat pump module. And one's like the thing that's inside your house that air conditions. And the other one's like the thing that's outside your house that blows hot air and it's noisy. So here's what happens on a sunny day. All during the day, the sun shines and cools off the cool tank and heats up the hot tank. And if the house needs to be cooled off, it gets its cool from the water to air exchanger in your HVAC system. And all this, of course, is controlled by your thermostat and some sophisticated electronics. And at the same time, all the heat that's extracted from your house goes into the hot tank. And that sophisticated controller circulates geothermal cooling to keep that hot tank at the perfect temperature for it to be most efficiently used to cool your house. And effectively, you're dumping that heat into your sump system to be absorbed by the earth in some way or another. Now, here's the neat part. In winter, starting in fall, when the house needs heat, coming now from the hot tank. House gets warm air from the water to air heat exchanger. And the hot tank, of course, gets its heat driven by the solar heat pump during the day by the solar panels, sucking heat back out of the earth in and about that sump tank and house foundation drainage system. And of course, this is all managed by that sophisticated controller that keeps the cold tank at the most effective temperature to make the most hot in the hot water tank when the sun shines. This is a picture of a compressor. This is the heart of the heat pump that does most of the work in our solar heat pump module. Okay, and the reason why we're calling this a solar air conditioning, actually it's geothermal solar, is that here in the Midwest and in most northern areas of the United States, it's going to be most effective as an air conditioner. We just don't get that much sun here in Wisconsin during the winter. So it really doesn't produce all that much heat. Its economic importance is greatest in the summer, spring, and fall. Another thing that might find out too is that all this heating and cooling of the sump pit is going to affect our basements. By the end of summer, we're going to have a pretty warm basement ready for fall. It'll be real comfortable down there until midwinter when it starts cooling off again because we need that heat that we put in there to keep the house warm. But all in all, and when it's all over with, it really doesn't matter because in Wisconsin, our basements are rather cool anyway. Okay, let's wrap this up with a little bit of recall. So we got our panel on a sunny day, runs a compressor which makes hot gas out of a cold liquid. The hot gas then condenses back into a liquid in the tube loops in the hot tank, heating the water in the tank. Then this liquid is expanded back to cold gas and run through the tube loops in the cold tank, making cold water. This happens all day and it's best with full sun. A sophisticated controller puts heat or cool into the home as needed during the day. And it also supplies the right tank with the geothermal cooling or heating to keep the whole system working in its best efficient mode. Because of the high efficiency of the solar air conditioning systems, paybacks of 3 to 5 years can be expected, depending upon tax credits and the quality of the geothermal sources. Connected on and with a good passive solar home design, a solar air conditioner can reduce costs to the utilities up to 90% and can be counted on for a full off-grid home design. Thank you for watching. We hope you are inspired to add a solar air conditioner to your home soon. You might find more information at our website, renewscience.com. And if you'd like to share this video, we'd like you to ask our permission. Just give us an email.